Hello, and welcome to tutorial number 34, I believe, of our series. And this one is also going to be a Grasshopper tutorial, as per usual, This time around, though, we will look into Millipede plugin for Grasshopper, and actually we will kind of try and merge Millipede with Monolith into one big happy family. We'll see how it goes. So Millipede in itself is a structural analysis program, right? So it's all about analyzing the structural loads and doing simulations structure-wise. And also it is discontinued, meaning that you can't really, it doesn't get updates anymore, but it is, in my opinion, one of the better free options out there for structural analysis. So, what can you do? Please, bird, stop. Let me, instead of talking, let me just show you. So, for instance, let's say we have let me just create a plane. I just have a plane here, just like that. And let me grab its control points and just move two of these points up to have this paraboloid shape, something like that. Right? So we have this this form here, and we want to analyze it structurally. So first of all, I will reference it in bird. Jesus, I will reference it into Grasshopper as a brep. There we go. Is that one? Or as a surface, doesn't matter. It's a single surface. And I will convert it into a mesh because Millipede really wants you to work with meshes. So I will use a tool that's called mesh surface. Right here. Just like that. And let me hide the brep component. So here you can see the resolution with which we're dealing. I will increase the resolution a little bit to give it more, like a better chance of calculating accurately. So by default, the resolution is 5 by 5. Let's go for 20 by 20. Yeah, I think that's good enough. So we have this, polygonal grid here. Okay, so that's our mesh. And now with Millipede, one of the ways of how you can work with it is by inputting a mesh and calculating loads flowing through that mesh. So that's FE system, right? It's right here. I will completely skip the eigen system portion of Millipede because we don't care about it. It's basically how things vibrate, I guess, what kind of frequencies are resonant. So it's good for bridges and stuff like that. So we will ignore it. We will immediately jump to FE system. FE means finite element system, meaning that it divides everything into these kind of smaller pieces that can be calculated more easily. And here we have FE frame element, FE mesh, finite mesh, finite element mesh, finite element quad shell, or frame curves. In this case, we are dealing with a mesh, so I just choose finite element mesh as my input. And it's gonna say that Millipede version has expired. By the way, if you can't, if you have troubles finding Millipede, where to download it, I will have it uploaded to my Patreon page, so you can just get it from there. And the link for the Patreon page is in the video description. So it asks us for a bunch of things. First one is meshes. So I do have my shell here, and I'll just connect my mesh to the meshes input. Second one is material. So I'll just go to the stock tab here, and I'll choose material from here, connect it. And by default, the material is set to be, actually, let me hide the profiler widget. By default, the material is set to be steel, but if I right-click it, I can choose any material that I want, carbon fiber, concrete, or whatever. You can also do custom materials, isotropic material, so you can do custom materials, but let's leave it as steel. So let's say this is a steel shell. Then we have thickness. So what kind of thickness does our shell have? Well, let's go for one, I don't know what. I believe, even though, this is an important thing. Even though we are working in millimeters, as you can see in the bottom, Millipede will calculate everything as if it was in meters. It doesn't give a shit, right? So now when I think about it, we are doing everything in meters, so let me do 0.2. A pretty thin shell. So it ignores the units of the Rhino file. Let me scale this down while we're at it. Just like that. This should be okay. Okay. And let me hide it. Okay, so next up, so this is 20 centimeters thick. It's still a pretty damn thick piece of steel. Let me do 10 centimeters. 10 centimeters, come on. There we go. And then we have area load and normal area load. These two I will not, I will leave these at 0. We don't want to preload the shell with certain stress. So it's not, it's in the resting position before we start the simulation. All right, so now we have our first component for the analysis, which is a shell right here, set up right here. Now, let's add some load points and some supporting points, right? So those are two things that we need. So those two are called finite element point load and finite element point supports. Let's just add both of them like that, and point supports like that. So our mesh, and let's start with the supports. We'll need to, it's not floating in space, even though it seems like, but we need to give it at least a few points where it can be anchored down, right? If you just give it one, it's going to kind of break. The bending moment is going to be insane. So we need to give it at least like 2, 3 would be ideal, but I will give it 2. So I will give it that point and that point. And to do that, all you need to do is just, create 2 points here and point here. They need to, the only thing about them, important thing I guess, is that they need to match with the corner of the polygons, right? So if you want the points, supporting point somewhere here, it does need to match with the vertice right here. So you could do that by just baking out the mesh and snapping to vertices and placing a point there, right? Anyway, we have 2 points. I will reference them in as a point component, right click, set multiple points. We have them referenced in, and I'll connect them. And this guy asks for one more input, which is a support type. And if I go to FE system, if I go to stock, here we have support type, right here. So I will drag it in, and I'll connect it like so. And it basically asks, this specifies, rather not asks, but specifies how is the supporting point constrained. So can it move in X? Or rather, is it locked in X direction? Is it locked in Y direction? Is it locked in Z direction? Can it rotate in X direction perhaps? Can it rotate in Y direction? Can it rotate in Z direction, right? So you don't need to just say that, oh, it's glued into place, right? It can be on a relatively free-flowing supported point rather than a nail, right? For now, I will just have it, all of it locked down, so it's as if this shell is nailed to the ground. So that's our second part, I guess, of the simulation. The third part is the loads, right? So we need to add some loads to it. Actually, we don't really need to, because we can just say that the structure should calculate its own weight, right? Self-weight. But just for shits and giggles, I want to add 2 more points. So I'll show selected, I will show my surface here. I will add these 2 points here. And these 2 guys will be 2 additional loads. So I will reference them in, set multiple points, hide, and I will connect them like so, right? So these 2 points are supporting and these 2 points are pushing down. Well, is it down? That's the question. Right now, there's no direction and no strength. So first of all, I need to say that, well, it's going to be in Z direction. Second of all, it's going to be negative, for sure. So it's going to be not up, but down. And then we specify a value. And what kind of value is that? Well, that's in newtons, right? And newtons is 9.8 newtons is 1 kilogram, which means, let's say 10. 10 newtons is 1 kilogram, which means this is a 10 centimeter shell. So let's say we are adding 100 kilos on each of these points, right? So that would be 1,000, or like 980 newtons, but let's say 1,000 newtons, just to keep the, on Earth, of course, just to keep the numbers right. Okay, so we have the load here, and let me hide those points. And hide those points as well. All right, we have 3 parts, and that's all you need for just a shell analysis. Then we can go to FEA system. This guy right here. It's also under FE system, FEA, Finite Element Analysis. FEA stands for Finite Element Analysis System. Here, which has model components. So we have 3 model components here. It has intersect-added curves. So if you're working with polylines that are intersecting each other, it will separate those curves on its own, which is nice. Then merge tolerances, minimum curve span, maximum curve span, and curve tolerance. So it's going to subdivide. Every curve is going to be subdivided into parts. We don't care about any of these inputs because we're dealing with just a mesh. We only care about the first input here. So I'll just connect first input. Holding down shift, I connect the second one. Holding down shift, I connect the third one. That's it. That's all we need to do, right? So now what we have here is we have a finite element system or model, doesn't matter, right? All of these parts are starting to work together. They're still not being analyzed, but now they are added together into one model, right? And now, to actually analyze them, I will go to Finite Element System tab, and I'll choose FE Solver, just like with Kangaroo. And it's a cool icon, I know. Like, I love this icon. This is the most stupid way of how to display wires, though. But what can you do? There's no way to turn it off. But this icon right here, I love it. Chimneys. Anyway, FE connects to FE, duh. Just like that, and it gets solved. Don't worry about it, it just gets solved. Then it's also self-weight coefficient, so it can calculate, does it calculate its own weight or does it not? Right now it's set to 1, meaning that its own weight is multiplied by 1, meaning it's calculating. Then we have beam optimization iterations, quad optimization iterations, optimization target, penalization, load case, is it all cases for load to be optimized against. I'm thinking how to explain this. basically you can optimize I will explain it in another tutorial, because this is this would become a separate video. So for now, let's just touch a little bit on it and not go too deep. So we are not going to optimize. Rather, we're just going to calculate, right, what we have here. And it does it automatically, so now it's calculated, right? We have the calculated FE model, we have the maximum deflection, meaning how much it bends, and it's a very low number, only 5 millimeters, and it has its own weight, right? And the weight is, I don't know how the weight is calculated. I guess it's just steel multiplied by volume, right? Yeah. Anyway, steel density multiplied by volume. Anyway, we have the calculated system output here, and let us do mesh visualization. So now let's start with mesh visualization. So this is where we get, and see how I'm moving down as I'm creating this definition. That's how you're intended to do. So we can do frame visualization, but we don't really, haven't worked with frames. We have mesh visualization though, like that. FE connects to FE again. Nothing really changes. Let me hide some stuff. It's too much stuff. So I hide everything except the final one. We do have deflection, so we can measure how it deflects. We do have plane for deflection, for the stress calculation, or stress calculation. We have the range. I have no idea what the range is. Meh. And we have show thickness option. So actually I can do toggle. Boolean toggle. Show thickness, yes. So this is the mesh with a thickness, and it's actually pretty damn thick. So let me say that the thickness should be 0.05, like half of that, because I want it to be pretty thin. Something like that. There we go. A thin shell. Now, when we made the shell thinner, the deflection should become bigger. And it has. So instead of 5 millimeters, it became 7. If I increase the value here to, let's go for 10,000, right? Here the deflection becomes, it's still pretty small. That's strange. Whatever. Whatever. If you guys know why it's still pretty small, then let me know. I'm no structural engineer. The cool thing about it is that we can right-click on this node right here and choose what kind of stress would we like to show, right? So I can show von Mises stress, for instance, right? I can show deflection, you know, which 2 points are the points where it deflects the most, and of course it's those 2 points here. That's where we are pushing it down. Then it has where is it? The not stiffness, bending moment. Bending moment is also very important, where it's, you know, how much it's bending. So we can color your mesh and then do this kind of analysis on the mesh pretty easily. What if we press step? No, it won't work. Doesn't matter. Okay, so that's that. There's one more thing that I want to show, and it's under FE system, there's stress lines output right here. Stress lines. And if I connect my FE output of the chimney thing, the solver, to the FE input here, also it asks me for seed points, so I will be cheeky about it and I'll just populate geometry with random 100 points, populate the mesh with random 100 points, and use those as my seeds, as my starting values. So it basically calculates, and I need to hide this, it calculates the stress from those points. And this is how it looks like with how the stress lines look like. And of course, there are two directions. Principal stress lines 1, principal stress lines 2. So there are two U and V directions on any surface, any shell. So let me do a preview, custom custom preview on this guy. And let me do another one on this guy, and this one is going to be black, while this one is going to be white. Let me hide that. What? Hello? Wireframe? Okay, sure. Whatever. But now you get it, right? So for the longest time, I had no idea, what to do with this. Yeah, cool. We get stress lines. I guess that's cool. But now, when Rhino 7 is almost out, I do have an idea. And that idea is, let me run it. I will just show you quickly, and then we'll move on to the next example. Because we have these stress lines, and usually you want topology of a mesh to follow the stress lines of the mesh before you make panels out of it, right? That just makes sense. So, and unfortunately Rhino 6 doesn't have that tool, so I'm loading up Rhino 7, and then for some reason it's not loading. Hello? Oh, okay. Updating toolbars, sure. So while it's doing that, let me increase the resolution a bit. So I'll double the resolution to 40, so that it's much smoother. So as you can see, the more polygons we have for the initial mesh, the smoother the output is going to be. Okay, so now it's loaded up. And now what I wanted to do here was, I will bake out this mesh, bake, default, okay. So I have that mesh, and I will also bake out these curves. And actually, should I bake out both of them? Or just one? Probably both of them, right? Yeah, probably both of them. So I'll bake out both of the curves. Default, bake, default, yeah. Cell CRV, group, so that they are neatly grouped. Now I will select both the mesh and the curves, Ctrl-C, copy, and Ctrl-V it into Rhino 7. And here, if you don't have Rhino 7, that's fine. You'll just, you'll just wait a little bit. This is not important, but this is something that I find quite interesting, so bear with me. So we have a mesh and we have the curves here, right? Let's go for shaded view. Mesh, curves, easy. I will choose to do, how is it called? Quad remesh. I will use quad remesh tool on this mesh, meaning that everything is going to be remeshed into rectangles. Enter. And here I have an option. First of all, I have an option to choose how many quads I want. 2000 seems to be okay. Adaptive, this is the size of the quads. Can they change the, not the size, but the amount of quads? Sure. And then it asks me to select curves. So I'll select curves, and I will choose all of my curves here, and I'll hit enter. Hit preview. Well, preview will not really help me. Actually, it does. I'll hit OK. Okay, and that's it, right? We have just used quad remesher to create a mesh right here. So this mesh, these polygons, it doesn't look nice, of course. We will need to kind of mess around with it a bit and then make it nicer. we would need to do, but it is a cool principle. So which means that we can take it, Control X, and copy it back into our Rhino 6, right? And then do some funky stuff with it. For instance, oh wait, display mesh wires. There we go. So here in Rhino 6, I can reference it in as a mesh. Set one mesh, sure. I can take each boundary. How is it called? Viewer bird, extract, face polylines. I can take each polyline from this mesh. I can say scale down that polyline to its center point, so polygon center, just like that, by 0.9, something like that. All right. And then we have the original one and the scaled version, which means we can loft between these. And let me just do a merge. Let's graft. Just you do need to separate them into separate branches. So you just right click and choose graft. And then let's plug one into D1, the second one into D2. Don't need anything else. Let's see. Yeah, everything seems to be clear. And just lock them together. So now we're starting to build a poly surface rather than a mesh. Let me hide this, right? Or rather, a framework for this whole thing to take shape, right? With topology that follows the curvature of the stress lines. I find this interesting, and I find this something that is quite important, because topology which follows the stress lines should make the mesh stronger. That's just my take, because then we can do we offset, do we extrude? That's harsh. Let's do this instead. Offset mesh. Let's do offset mesh on this guy. Ooh, no. Let's go to viewer birds. Viewer bird, hello? Viewer bird offset mesh, like that, distance 0.1, something like that. We can do fancier stuff, you know, it becomes thicker in the bottom and then shit like that, but we don't care. And I will repeat the same thing for the offset mesh as well. Like that. So we have the top and the bottom, and then I know that these two guys, if I loft between this and this, it will create the inner ring. Yeah, and that should be it, right? Yeah, let's try. Why not? Merge this list with this list. How does it look like? It looks bad. So when things look bad, you just simplify them and then double check. Now they don't look bad. We do loft. We wait. It works. And we have our form here. And let us just... Do we just bake everything out and join? Let's just merge everything into one big happy family. So flatten it out. By happy family, I mean flattening it out and using brep join. And just hoping that it's not gonna break. So after waiting a while, this got calculated. I believe it took 6 seconds? No, it didn't take 6 seconds. It took longer, but perhaps it's just the preview. And now we have a thickened version of it, which we can, it's a single brep, so I can just bake it out. Wait for it to do the meshing. Oh, come on. Really? Takes you that long? Sure. So after waiting a while, this got calculated. I believe it took 6 seconds? No, it didn't take 6 seconds. It took longer, but perhaps it's just the preview. And now we have a thickened version of it, which we can, it's a single brep, so I can just bake it out. Wait for it to do the meshing. Oh, come on. Really? All right. So for my next trick, let's try to do something more interesting. So I will take these guys and I will just maybe delete or hide. Maybe I'll just move them to the side and then hide them. And now, let me disable preview of that. Now let's do something, where's my Millipede? Let's do something with an actual design and actual optimization. I know I said that it's going to be in another video, but I really want to push this out and then show you guys how to do it. So let's do what everyone is doing, a chair, I guess, a parametric chair. So I'm just going to, maybe, how do we do this? Maybe let's create a plane, starting from 0, and I'll just draw, sure, a plane like that. And I will rebuild it to have, let's say 3 by 5 points. That's 4 by 5. Let's go for 4 by 6 points. Hit OK. Fn F10 or just F10 probably in your case. Before, let's just rotate this bad boy up so that it's vertical, and let's kind of manipulate the point so that it starts looking like a chair. So something like this, something like that. That is definitely not a chair. Let's try more, like that. So now I'm just messing around with the profile of it, and then we'll maybe do something nice with it. Perhaps it can, this guy can twist. Should it twist? Yeah, let's do something funky. Twists 90 degrees. This one moves up, this one moves down. So as you can see, it starts slowly but surely looking like an actual, something you can sit on at least. And maybe let's have a little bit of a dip here. So I'll just grab these 4 middle points here, just make it dip a bit. Let me change this to shaded view so that you can see better. Something like that. Why not? And also, while we're at it, let me move this to the side like that. And in front. Let me zoom into it so that it's easier for you guys to see. So I'm just messing around with some design. So that, and let's do an S-curve here for stability. This is definitely not, it is not a stable chair, that's for sure. But it is what it is, right? I kind of like it. Looks fine. Actually, let's solve the top as well. I will just bring these two guys back a bit to make it bend. Take all of these, bring them back, like that. Okay, so we have a chair design. And now, just give me a second. So now we will bring it into Grasshopper. And I might reuse some of these parts. Yeah, I might as well. So let me grab the first part where we have the B-rep. We create a mesh from it, and we construct the FE mesh, the finite element mesh frame from it with steel and some thickness attached to it. Let us do that. Just like so. And I will, of course, reference in our new chair as that B-rep, right? And for that, I actually want to have these polygons as close to being rectangular or square as possible, so I will be using 2 sliders rather than 1. Let's say the U count is 20. Come on. 20. And the V count is, let's go for 60. Something like that. That's good. Let me hide it, or actually let's not hide it. Let's keep looking at it. Because now I will not be using point loads and point supports. Rather, I will be using a load region and support region, where support boundaries are changed. Hello? We'll figure it out. For now, let's do a load region right here. Okay, so it asks us to give it a boundary, right? Where, from which area is the load going to kind of be pushed on, like so where is the load going to be placed? And I will say, yeah, let's go for the top of the chair, right? So I will just say top. And for that, I will just create a box. Should probably do that in the top view. Just like that, position it. And in the front view, I will move it to here. So this is a region in which load happens, right? Let me reference it in as a B-rep. Set one B-rep, just like that. That's our boundary. So next up, let's apply some actual load to it. And you have 4 different ways of how you can apply load. In this case, I will choose aerial normal, right? So basically, it doesn't apply load straight down, but rather it applies it in a normal direction of the chair, right? So backwards. So let's do that. And here I will just specify, how do we do that? Well, first of all, I want to see the normals of it. So let me bake out the mesh just like that. And I will go to display. I'll choose color back faces to be turned on. And now I can see what's the front face and what's the back face, right? So actually the back face is here. So if we use a positive value, that means all of the stress, all of the vectors are going to go in this view towards the left, right? Kind of towards the left, which works for us. So that's good. That was just me, double checking the direction. So for aerial normal load, I will use a positive value, and I'll just do, let's go for 800 newtons. I believe it's in newtons. Maybe it's not. I don't know. Doesn't matter. Okay. So we have the second one. That's the load. And now for the third one, let's actually use that material properties. Oh, sorry. Material support type region. this node right here, which also asks us for a boundary. So I need another box, or actually let's cheat a bit, and I will just show that box, copy it down, and make sure that it's intersecting with the base, with the whole base of the chair, just like that. Let me create a brep component, right click on it, set one brep, set that box, connect it, we're done. And hide it. And actually should I hide both of these? For now I'll keep the boxes just so that it's easier for you to see where the load region is and where the support region is. Okay, so now for the support type, that's the same thing as we used here. So I will just go to stock, support type, just straight up connect it. No need to do anything else. And then we have amend existing supports. True, sure. We ignore it. It's not necessary. Okay, so we have three components: the frame itself, the shell itself, the load region, and the support region. So we do the same thing, right? We use the FEA system, and holding down the shift key, we just connect all of them. No need to do anything else with the FEA system component here. Then we use FE solver here and connect FE output to FE input here. The solver solves it, I guess. But now I actually want to, I don't just want to look at it, you know, how the stress goes through it. I actually want to optimize it. So this is where it gets interesting. Right? We want to optimize the structure, or rather to see how the structure could be optimized, which parts could be thickened and which parts shouldn't be thickened. So let's do that. Self-weight coefficient 1, I always leave it at 1, that's fine. Beam optimization iterations, that's whatever, we're not using beams. But quad optimization iterations, we are using quad mesh, right? So here we need to have more than 0. So I will do, let's do 12. So 12 times optimized. And you can see immediately when I plug in 12, it will do this optimization 12 times, right? So it's kind of recalculating the optimizations, the optimization. And you'll see what I mean by that in just a second once we start coloring the mesh. So the next output is optimization target, and that target is right now 0.3, meaning that it should remove 70% of the material and leave only 30%. Sure, let's see how it looks like with 0.3, that's fine. Optimization penalization is set to 2. I have no idea what that means, but 2 usually works quite well, so let's keep it. Load case, all cases, that's whatever. We don't care about those. Okay, so we do have an optimized structure, an output of an optimized structure here in FE, and I can go and take a look at, I believe it's mesh visualization straight up. Can just connect it like so, or is it not? Maybe it's not. Oops, my bad. Is it quad results? It might be quad results. No, this is a different thing. Just a second. I need to do this on my own. Just give me a second. Okay, we're back. So it was indeed this mesh right here. Let me hide this for just a second, and let's actually hide everything except this little node here, the last one. So I've hidden everything, and we have this node here. And again, you can look at stress values, right? You can look at deflection values, right? You can look at normal displacement values, I guess. And the key thing here is the stiffness factor. That's the thing that we want to see. And right now it's just gives us a white output, but if I choose to, and here you will see it better, this says step and this says reset. If I click on the step button, it's going to calculate again. So it's going to optimize once more. So it turns gray, nothing interesting. Let's try again. And now things are starting to get interesting, right? So this is the stiffness factor. Let's try again. So I'm optimizing it one more step. And with every step it becomes brighter and brighter. So this is, how much is it? It's 30%, right? These white spots. If I change this to 0.2, or let's go for even less, 0.15. Let's see. It's going to become right here. It's going to, these white parts are going to become smaller, which is what we want. Just to be clear. So that happens. Let's try again. Maybe I should have used the reset button. No, we'll see. Like that. And like that, right? So it's starting to become this kind of a weird form here. Actually, this is kind of a boring shape. So let me, or boring pattern. So let me just show my surface here and play around with them, mess around with the control points a little bit to make it more interesting. I'll just grab these two and move them back. Just to see if it helps or not. It's probably not gonna help, but maybe. So now that the form looks like that, and let's use a few more steps on it, and it should do the trick. And I will not be messing around with it anymore. You can do that on your own. But now at least the pattern starts to emerge. A little bit more interesting pattern is starting to emerge. Okay, step one more time. So the white spots are where the chair needs to become more stiffer, right? And black parts are not. So we can work with that. We can work with those colors because this mesh, basically every vertice has a color, right? We can work with those colors and create an offset of this mesh, right? So if I deconstruct, oh, by the way, before we do that, let me also show what this does, right? It's a bunch of planes, but with this one, I just populated it with random points and used the stress lines. With these random planes, not random, but with these planes that we get here, principal stress frames, we can actually get a much more accurate, not accurate, but precise, which is a synonym, I guess, analysis by just connecting FE to FE, PS to P, and then we get this pattern right here, right? Let's optimize it once more, and then you will see that the pattern kind of flows a little bit better with more optimizations. Yeah, so it's starting to clean up bit by bit. Okay, So we have that. Don't care about it actually, but I do care about the mesh and its colors. So let me deconstruct the mesh, right? So we have the vertices, we have the face information, and we have the colors. And all of these colors, they have basically the God damn it, sorry. Basically, the brighter a color is, and it's attached to each vertice. A brighter each color is, the closer it is going to get to 255, number 255. And actually, it's not 255, but 255, 255, 255. That's RGB values. So, and also we have normals, which is also very, very good. So what we're going to do is we are going to take these vertices and we're going to move them. And we're going to move them along this, along their normal direction. So yeah, we'll just use this vector, but the strength of how much we move them will be dictated by how bright the vertex is. So I will say amplitude. That's how you add strength to a vector. And you can see right now the amplitude is 1, so it just does that. Amplitude, and the amplitude is derived from the color, so so let us say text split. So we have the colors and we split them, and what is the separating character? Well, if I look at the color output, it's a comma, right? So if my separating character is a comma, I just wrote a comma in the panel. There you go, you can see it now. That's a comma. Now these values are going to be split into 3 outputs. And these are grayscale values, so it doesn't matter which one we choose. I will just get the first one. List item, just like that. It gives me the first, basically the first number in RGB value. So we're just recording the red channel. That doesn't matter. And I'll just flatten it out to have everything in the same list. If I were to connect them right now, like so, you can see that there's a lot of mess that's going on. That's because some points are being moved by 255 units, and that's way too much, right? So I need to solve that problem, and I can solve that by remapping the numbers, these numbers, where my source domain is, I know by default that it's between 0 to 255. It's somewhere between 0 and 255. And it's going to be remapped to a new domain, which is going to be the smallest value by how much we move, is the thinnest part of the chair. So let's say that's going to be 0.1. 2, and the largest value is going to be 1, like that. Oh yeah, and we kind of need to connect the output of remap to the amplitude, of course. So now you can see that where we have the white pixels, right, or white vertices, not pixels, it bulges out, right? And the problem now that we have is that this is a mesh, and this is just a bunch of points, right? Just a bunch of moved points. So we need to rebuild a new mesh, right? And we can do that by just using construct mesh tool, which asks us for the points. So we will use the moved points for it, like that. It asks us for the face information, and we do have face information here. So we just connect it straight up like that, and it already works, right? So we don't even need to add any more values to it. Like that. And it doesn't look that great, I know, but yeah, what can you do? And this is too wide of a bend. That I also know. By the way, if you want to color them, you can. You just connect color to color information, and now the backside is going to be colored as well. And all you need to do to kind of close it off is just, bake it out and loft between the two meshes, and it's just going to be lofted. I will not be doing that for you. You can do that on your own. So let's see different patterns that we can get. Or actually, let's just merge. Let's merge the original mesh from here with the offset mesh here. So all we did was an offset, basically, a fancy offset to say the least. I'll just use mesh join. That is text join, that's incorrect. Mesh join. There we go. Flatten out the merge output. And let me bake this out. Look at it in shaded view. It's kind of, that part is in the way. And this is how it looks like in the shaded view. So I can actually, yeah, why not? Duplicate border, loft. Sure. Let's go for Arctic view. All right, I have a freaking solid color turned on. Use application settings. There we go. So we end up with this kind of a bulky chair. Now when I think about it, perhaps it should be other way around. No, it shouldn't. So it is these parts that need reinforcement for sure. So these become thicker. Okay, let's quickly do another design. Show selected. That surface right there, and let me hide the mesh for now, or rather hide everything for now, just so that we can mess around with the design, and I will just show you, how it all works. Let's grab the control points and just do something like that. Oh right, and I need to kill it. I will disable the solver here just so that it doesn't recalculate every time I move the control points. Like that, maybe this guy can come back, and this now is a very steep seam, so I will bring it back, just like this, like that. So it's a little bit calmer here, something like that. Bring this back. Okay, this doesn't look like a chair at all, so let's do this. Let's do that. Okay, can you sit in it? It seems that you can. Maybe it needs to be a little bit wider here. Okay, a little bit off center, but that's fine. Let's look at these two blocks. Yeah, they still are fine. Seems to be okay. And actually, this one I will say it should also eat the part where your ass is gonna touch, right? So only this portion now is going to be optimized. Maybe a little bit further. Hide it. Yeah, that sounds about right. Or looks about right. Let me hide everything and try again. So I will enable this. It's going to do its calculations. And it's, as you can see, it's running quite fast. Let's see just the chair. Okay, so we need to do it once more. Okay, so now we are getting some interesting patterns. Actually, I don't like it. 0.3. Let's do it this way. Because 0.3 will merge these blobs more. Yeah, that's what I want to see. So let's optimize it once more. And then it should be good to go. Okay. So now let's look at it once more with the offsetted version. And now this is the chair that we get. This is an overkill, I would say, like 0.1 to 1. I would say 0.1 to 0.5 is much more reasonable, you know, change in thickness. But it is what it is. And then, actually, can we just, is there like a mesh loft option? Parameter mesh loft. Create a lofted mesh through a set of section curves from the domain dividing U and V parameter. No. Bitmap loft. Mesh loft. Yeah, what am I? Creates a mesh from the control points and input curves with multiple methods for them. Yeah, sure. Let's do this. So I believe this one comes from Mesh Plus plugin, which you can also download from Food for Rhino. I need naked earburst naked boundary of these two meshes, and they will come in here, and yeah, they just get lofted immediately. That was easy. Face type quad, I will just say 0 or quad gets cleaned up. Yeah, that's it. Mesh join up the original mesh with the lofted mesh right here. It loses color information, but that's fine. We don't care about it. And let's do some Catmull-Clark shenanigans to it. Level 1 seems to be okay. I'll just bake it out. Default layer. It's inside out, but that's fine. We just flip it. Ooh, we do unify. Yeah, we can do it here, actually. Unify mesh. So we just unify mesh normals. You can also use viewer birds extract, unify face windings, but there was a unify mesh normals. What do you mean? Maybe there wasn't. Whatever. Unify mesh normals. Oh, mesh unify normals. Sure. So you can do that. Oh, you can do that. And now let's bake this out. Take a look at it again. Oh, it still doesn't work. Okay, let's clean it up in Rhino then. Unify mesh normals. It works in Rhino. I don't know. Sometimes it's weird. So now it's all rounded, all smooth. If I look at it in the Arctic view, it kind of looks like that. Let's throw an EMAP on it, just to see how it looks like. And you can see some parts are more bulky, others are not that bulky. So that's structural optimization 101. I think that's, or actually let me keep it. Show selected, I'll show everything, and I'll just move it to the side. Is it going to, yeah, of course it's going to start optimizing again, but We don't care. We will just close it. All right, let's hide and let's do the one last thing that I wanted to do this video. So group this bad boy up. This one is done as well. I will actually, should I disable them? Yeah, I should disable them, right? Disable and disable. So if you want to use it, this is for my Patreons, if you want to use these, you'll need to enable the components, right? Just select them, middle mouse button, enable. All right. One last trick with Millipede. 3D. TopoStruct 3D, right? It's a pretty cool one. So for this one, we need a 3D boundary region. And of course I will, show more, but not in this tutorial. I don't want it to be like a 5-hour tutorial. So we need a boundary region. So we are going to work with voxels. For boundary region, I will just create a box, and actually I can, let's do a box in Grasshopper, box, center box. Like that, and the size of the box is, let's see, 100 by 100 by 100. Oh, actually it's going to be 200 by 200 by 200. That's way too big. Let's say, sure, something like that. Because I want to have all of the elements kind of similar size. Then it asks, is it a void or not a void? So I say it's not a void, so this is false, right? This is a solid object. And how do we do that? So we need a load region and support region. We will need these two for sure. Load region, support region, right? And actually for this box, I want, it doesn't need to be a cube. So I want the y value to be 0.8. Okay, let's do 2 then, not 0.8. Yeah, something like that. Maybe wider, twice as wide. 4. Okay, that's good. So now load region. I need to specify which part of this box receives a load, right? A certain amount of load. And actually I want to make it longer, so let me do 26 here, something like that. So for that, I will actually create a box, just like this. And I will say that a load is going to come in like this. And I will just say brep, select the box, right click, set one brep. That's my boundary. Okay. And load type, I believe, no, it's just load. So by default, the load is set to be -1 in z direction, so it's kind of going down, and that's fine. That's what we want. So I won't be messing around with it with this one. Then we have support region. So I will say, let me just copy this box. I like this box. Let me copy this box, and I will say that this guy is being supported in 2 places. One place is here, one area is here, and the other area is here, right? So I will select brep, like that, set multiple, and I'll just select these 2 boxes here. There we go. Support type, we all know this. We go to stock, choose the support type, just connect it. Everything is locked in place, we don't care. And amend supports, existing supports, we don't care. Okay, so now we don't use an FEA system, rather we use TopoStruct 3D model, right? Let me connect all 3 of these guys here, right? So everything is merged. We have a system now. And it asks us for, hello, why are you red? Are you red because of this? No. Are you red because of this? Yes. Are you now not red anymore? No, you are still red. Are you red because you don't understand what a box is and you actually want it to be a brep? Yes, you are. Okay, so we do need to convert the box into a brep, whatever. So it false, it's not a void, and now let's reconnect everything. We can continue. So this guy basically takes our box and converts it, kind of cuts it into small pieces, voxels, so it voxelizes it. And this is its resolution. So right now the resolution is set to 12, and I will do something like 16 maybe. So more. So it's basically 16 by 16 by 16. And you can kind of see these. This is the vectors for the load, and these are the support marks right here. Actually, I can hide the brep so that it's easier for you guys to see. And if I move the load box here, these guys change, right? Okay, so we have a system here. We have the cell centers here, and we have the size of each cell, which is 3 units, whatever. I will then use TopoStruct 3D Solver, which is a big boy. I'll connect my FE model to it, and it immediately starts, chugging along. But we still need a few more, a few things to change. So self-weight coefficient, for this one, I will keep it at 0. I don't care about self-weight. I only care about it reacting to the supports and the loads. Then we have optimization iterations. Here I will actually specify 4, something like that. So it does its magic. So it does it 4 times, and goddamn, I'm running a 4K screen and it's freaking out. That's step, that's analysis, I believe, that's reset, that's delete, that's subdivide, I don't know, maybe. We only care about step analysis and reset. I don't use other two. Okay. So next up, we have smoothing factor, we have penalization again, we have target density. Target density is important, so right now it's set to be 40%. I will actually force it to be less, 20%. That's my target density. Then it asks me for initial densities, we don't care. Minimum density, we don't care. Delete threshold, we don't care. Periodic, we don't care. So it's basically only these 3 inputs or 4 inputs that we care about. Okay, we have the FE output. Let's actually see what it gives us. So for this one, we will need to use a 3D ISO mesh, I believe. We will see. I believe it's 3D ISO mesh output here, like that. And then we will need to specify an ISO value, or am I wrong? What's a D? D is deflection. Let's specify an ISO value, 0.1. So the 0.1 ISO value looks like that. Now we don't want to see the box anymore. So it's the ISO value is always between 0 and 1. So let me do 0.5. Connect it. Kind of drag it back. So you can see how it works, right? And already with only 4 optimization iterations, you can see that the result is becoming a bit more clear. So let's run more iterations. More. So now the resolution is becoming a bit tricky, right? You can see that the resolution is not that great. And also you can kind of right click on this ISO mesh value, and you can say, well, I want to see the stiffness factor, or I want to see the deflection, the maximum deflection. Of course, it's that part. And or I want to see the principal stress. You can do that. So now I will come back to my resolution settings, and I will double it to 32. And it's going to take a little bit of time, right? It takes a while to kind of calculate something that has this amount of resolution. But now the output is going to be much more precise once I kind of nail down the ISO value. Can I use subdivide? Ooh, that was a very big mistake. Let me use delete, reset, and do step. Do analysis. Oh no. Oh no, I don't know what I did. Reset step. Help. What's that? If this happens, I usually disable this and enable this again. No, it still doesn't happen. Okay, let's awkward tutorial time. Let's create a new tool here and let's do that again. Like connect everything again. And this time I will choose, let's go for 8 optimization samples. And let's connect slider 0.2 to our target. FE to FE, choose step. It crashed. No, it didn't. I just needed to close it. Now it works. Now it's freaking out. Now it's crashing. Oh no. Yikes. Okay, let me pause the video and see if I can kind of bring back at least a little bit of what I have saved. Okay, so even when it's crashing, let me turn on Grasshopper. Even when it's crashing, it's still doing quite well. So you can save it. That's all I want. Yeah, Millipede. And now, now it's going to be optimizing. Let's wait a bit. It's going to do it 8 times. So it takes a while. So this is something that students really like to do because it's easy to set up and you get really fancy forms and you can see that it's highly optimized and all of that jazz. So it's nice. So you end up getting these kind of cool shapes. All right. Let's do that again. So apparently don't press these 3 buttons, just press step, analysis, or reset. The more you know. Come on, keep going. Okay, there we go. That's what I wanted to see, right? Looks cool. Let's do it one last time. So you do need to run it through quite a few iterations for it to start showing its, full potential, but you end up with something that is really cool. And leaving only 20% of material is definitely pushing the envelope, to say the least. So I'm quite impressed that it still manages to kind of keep the whole shape together. Oh. It's starting to crash, but not to worry. We will just decrease the ISO value until it reconnects. And this is the form that we get. And I can run Catmull Clark on it, I believe. And it's going to become a little bit softer, just like that. Bake it out. Move it to the side. That's it, guys. That's it. So this is the third one. I will also disable it, just so that you don't need to worry about it. Let's see, can we make it prettier? Usually, in real world, when you get this form, you don't really, wait, why is this transparent? Flip. There we go. When you get this form, usually you don't really use it. You model on top of it, right? So you remodel the shape on top of an optimized form. so me using it would be weird. Let me just smooth it out a bit. How much does it smooth? Quite a bit. Yeah, that's good. That's good. That looks fine. Okay, and let's go for Arctic view. That's our optimized bracket that holds some box. That's it. That is it. Let me show all of these files again. Move to the side. All of these files will be available for you to download if you're a Patreon supporter. So link in the video description below on how to become one. I'll also add a Millipede plugin files there if you are lazy and don't want to search the internet for them, because it seems like they're kind of hard to find these days. And other than that, check out the streams. I will be streaming today as well, so hopefully I'll see you there.